space-time has a geometry. He thinks to himself, well, maybe it's the actual shape of space-time itself that is giving rise to gravity. So in this video, we're going to be talking about a new study that confirms a relatively old theory by Albert Einstein, the so-called frame dragging theory. But I think I have to explain it to you first, but you can check out the study in the description below too. So, what exactly is this so-called frame dragging? White dwarfs behave very differently than normal matter. Take planets and stars. They become bigger when they gain mass. Einstein's general theory of relativity is the source of the concept of frame dragging. More officially, it's known as the Lense-Thirring precession, named after the two scientists who actually created this idea back in 1918. And although it's really hard to envision it, it's also not very tough to understand. Essentially, when a big body spins around, it will drag the space-time around it with itself. Here is a very basic graphic simulation to help you comprehend the effect. This object in the middle is massive, and it spins, and as it rotates, it literally drags with itself all of the actual space-time around it. And this causes this frame dragging effect that you can notice in this simulation. One of the more exotic examples from some of the recent movies is actually in Interstellar, where the effects of frame dragging of the ultramassive black hole called Gargantua create so much space-time stretching that one of the planets starts experiencing really dramatic time dilation effects. And this was the object known as Miller's planet. If you've seen the movie, you kind of maybe know what I'm talking about. But these effects don't simply occur around really huge black holes. They also obviously exist around Earth, since Earth spins. But because Earth is way less massive than a typical black hole, and it doesn't spin near the speed of light, the effects are really minuscule. We didn't really know if they were real until back in 2004 to 2005. We launched a satellite known as Gravity Probe B, inside of which there was a very interesting device, a type of multidimensional gyroscope that as it moved around the planet and as the actual frame dragging occurred, was able to very precisely measure how much frame dragging our planet was producing. And as you can probably imagine, the numbers were extremely minuscule. But this was the first official scientific proof that frame dragging is not just a theoretical concept. It's an actual physical concept that exists out there. But today, we'll talk about another really extreme example that scientists were able to just discover, once again confirming Einstein's ideas and the ideas by Joseph Lense and Hans Thirring, the two scientists who actually proposed the idea to begin with. And this new discovery comes from a system of very unique, very unusual objects, these so-called compact objects, basically a white dwarf and a neutron star. In a nutshell, this is what, if you were to simulate the system, it would look like. We have the pulsar, or the neutron star, right there, the object closest to us. And in the back, you're seeing a white dwarf. If you remember, neutron stars usually form when a relatively massive star goes supernova and leaves behind a kind of a remnant. In this case, this remnant is approximately 2 1/2 masses of the Sun and it spins about 2.5 times per second. White dwarfs, on the other hand, are formed by slightly smaller, in terms of mass, stars, and our Sun, for example, will also become a white dwarf. But both of these stars are very, very dense. The white dwarf is not as dense as the neutron star, simply because it has less mass in a much larger volume. In comparison, the neutron star here has more mass in a very, very small amount of space. So the size of this object, the white dwarf, is about, well, similar to our planet Earth, actually. Here's what Earth looks like for comparison. And a typical pulsar is about 20 kilometers in diameter. So this is the size of a relatively large city. And the scientists behind this paper started to observe these two objects roughly around 20 years ago. In other words, they've collected about 20 years of very accurate data on how these objects orbit around one another. And obviously, they've discovered something a little bit unusual. The pulsar that was orbiting around the white dwarf was actually doing this. It was tumbling, and way too much. It was kind of moving around in a very unusual, very unpredictable way. At least unpredictable until they figured out what was going on there. Because normally, when a typical pulsar spins, you're supposed to see something like this. Here are another two very famous pulsars. And this is without the Einstein's ideas in there. So notice how the actual light beam always seems to cross the same location in space. Now the thing is, these two pulsars are much farther away from each other, and so they don't experience the same frame dragging effect. But because pulsars are so accurate and so predictable, we've even been thinking about using them as a kind of an atomic clock. Much more precise than an atomic clock. The way that they pulse is extremely precise. Now, what about this other system here? Something was causing this pulsar to tumble and not be as predictable. But eventually, they figured out that there was a pattern. And this pattern was actually related to the frame dragging effect. In other words, they realized that the white dwarf was causing the pulsar to actually tumble because it was dragging so much space around itself. Here is kind of what all of this looks like. Notice how as the white dwarf spins, the space around itself causes the orbit of the neutron star or the pulsar to slightly shift once in a while. And this shift is very predictable and easily observable using the theories I previously mentioned. And now that they were able to explain what's causing this unusual tumbling of the pulsar, they had to explain how this white dwarf acquired this unusual, very fast spin. And so they started to look around for various ideas on what could have caused the white dwarf to spin so fast that it produced these observable effects. These effects were essentially about 100 million times stronger than the effects that the satellite observed around planet Earth. And this is quite significant. This is essentially a very distinctive proof of Einstein's theories, and of course, the most accurate proof that Lense-Thirring ideas are also correct. And ironically, neither Lense-Thirring nor Einstein believed that we would ever prove this, because they never thought it'd be possible. But thanks to the advances of modern technology and this beautiful telescope that you see here, we were able to finally prove this once and for all. So, what exactly do we think happened here? Well, first of all, These stars are compact stars, but they're also remnants. They used to be actual big stars similar to our Sun. The star that turned into a white dwarf was probably a little bit more massive than the Sun, probably about 2 to 3 masses of the Sun, whereas the star that became the neutron star was somewhat equivalent to, I guess, the star known as Deneb. Here, the mass was probably about 12 to maybe 15 masses of the Sun. These two stars very likely orbited around one another, and the scientists behind this paper believe that the Sun-like object became a white dwarf first. So, basically, this turned into a compact object not so different from the very famous white dwarf known as Sirius B. So, as it transformed into the white dwarf, the other larger star also started to expand and loosen its outer shell. And as it became bigger and bigger, some of its mass started to fall into the white dwarf. And the thing is, we know that when the compact objects receive mass, like for example through the accretion disk, they often start spinning up. They actually increase their rotation. This is how we believe so many various pulsars became extremely fast spinning, the so-called millisecond pulsars, essentially allowing these pulsars to spin so fast that if you were to stand on their surface, you would be moving at about a quarter of the speed of light. But in this case, the spinning happened to the white dwarf. So the white dwarf was spinning really, really fast. And because this other star was still expanding, eventually it reached the point where its envelope was touching the white dwarf. And this, of course, resulted in the white dwarf suddenly being bombarded with a lot more mass, increasing its spin even more. But most importantly, it actually started losing orbital speed. And this, of course, means that it slowly starts moving closer and closer into the star itself. And it's very likely that at some point it actually entered the star. And we can't really simulate this very easily here, but I'm going to try. So now we're sort of inside the star. And as this white dwarf consumed more and more mass, it spun up even faster while moving closer and closer to the central region of the larger star. And at some point, something very likely triggered the supernova, while at the same time leaving the remnant behind, with the white dwarf and the pulsar being the only leftovers. And this is when the white dwarf was already spinning really fast, and the pulsar was orbiting very, very close to the white dwarf, creating the system that we just observed for the past 20 years. But the thing is, it's not a particularly satisfying explanation. And one of the biggest problems that I'm having with this is why is it that the white dwarf happened before the pulsar? Normally, neutron stars or pulsars come from much larger, more massive stars, which often live way less than typical stars like our Sun that turn into white dwarfs. Technically, the pulsar should have appeared first, not the other way around. So, here there are still quite a lot of mysteries in this system that we need to resolve. There's a possibility that maybe this is actually a captured object from another star system, and this is something we'll need to discover in some of the future studies. And at the same time, we're still not sure what made the pulsar spin relatively fast as well. Something must have given mass as well, in order for both objects to be spun up so much. In terms of the rotation speed, as I mentioned previously, the pulsar here spins once every 2.5 seconds, whereas the white dwarf takes approximately 200 seconds to spin once. But since the size is so different for both of these objects, the white dwarf definitely received a lot more mass to be spun up so much. But for now, unfortunately, that's all we know about this system. And hopefully, some of the future studies will once and for all resolve the origin of this unusual system and how it came to be. But the most important discovery here is, of course, the confirmation of Einstein's ideas once again, and the most definitive proof of the so-called frame dragging effect that one day we'll be able to figure out how to use for practical purposes. But remember, 100 years ago, Einstein didn't even believe we'll ever discover this physically, and we just have. So imagine what's going to happen 100 years from now. We can only imagine what one day we'll be able to use this for. But anyway, until we learn more, or until other studies, that's really it. Check out the study in the description below. Subscribe if you still haven't. Share this with someone who loves learning about space and sciences. And come back tomorrow to learn something you may have not known before. But anyway, I'll see you tomorrow. Come back tomorrow to learn something else.